All right, so you want to know how to make robots move faster,
Yeah.
especially those with, like, more joints than they really need.
Right.
Like,
Yeah.
think about, like, a human arm, you know?
Mm-hmm.
It's got all this flexibility,
Yeah.
but all it really needs to do sometimes is just pick up a cup.
Right.
We're looking at a research paper today, and it's titled A Bi-Level Optimization Approach to Joint Trajectory Optimization for Redundant Manipulators.
Wow.
It sounds kind of intimidating,
It does.
but trust me, the idea is actually pretty clever.
Yeah, it really is. These robots with all their extra degrees of freedom, they're so versatile, but programming them for speed and precision is a huge challenge.
Yeah?
I mean, think about industrial robots. Like in a factory setting, time is money.
Totally.
So if we can optimize their movements, particularly for tasks that require a lot of precision, like 3D printing or laser cutting,
Mm-hmm.
the gains in efficiency could be massive.
Okay, so how does this paper approach that challenge? I'm really intrigued by this, like, bi-level idea.
So imagine this.
Okay,
You break the problem down into two levels.
right.
At the lower level,
Mm-hmm.
you figure out the absolute speed limit for each joint.
Okay.
Like how fast can it rotate or extend without,
Yeah,
breaking?
basically like finding the speed limit for each part of the robot's arm.
Exactly. And
Yeah.
the beauty of this is that for certain situations, this has what's called a closed form solution,
Oh, interesting.
meaning it's computationally very fast.
So that's good.
Yeah.
So we've got the speed limit for each part.
Right.
What happens at the higher level?
Okay, so the higher level is where things get really interesting.
Okay.
It takes those individual speed limits
Mm-hmm.
and it uses them to choreograph the smoothest, most efficient path for the robot's end effector.
Okay.
That's the part that actually interacts with the world.
Oh, yeah.
It makes sure that the robot hits all the required points, pinpoint accuracy,
Right.
but in the fastest possible time.
So it's not just about how fast each joint can move on its own, but how they all move together.
Yeah,
Like a perfectly synchronized dance.
precisely. And, one of the key insights from this research
Yeah.
is that sometimes just slightly adjusting the robot's orientation
Hmm.
can significantly speed up movement along the same path.
Wait, really?
Yeah.
So it's not just about the path itself,
Uh-huh.
but about how the robot is positioned along that path.
Exactly. They demonstrate this with a fan blade example.
Okay.
It turns out smoother joint movements, which you can achieve by making these subtle shifts in the robot's overall posture,
Interesting.
translate to much faster task completion.
So it's like finding like the most aerodynamic pose for the robot as it moves along the path.
That's a good way to put it, yeah.
That's a cool finding.
It is. And this bi-level approach doesn't just improve speed,
Right.
it also slashes the computation time needed to find these optimal paths,
Okay.
which is a game changer in real-world scenarios.
Yeah. Because in a factory, like shaving off even seconds
Yeah.
can add up to significant savings
Oh,
over time.
Right.
But did they actually test this out, or was it all theoretical?
Oh, they put it to the test.
Okay.
Both in simulations and on a real UR-10E robot arm.
Oh, cool.
And the results were impressive.
Okay, I'm hooked.
All right.
Tell me more about those experiments.
So they started with simulations.
Okay.
Focusing on a scenario where the robot had to trace the edge of a fan blade,
Okay.
a task that definitely benefits from speed optimization.
Mm-hmm.
And to make it challenging, they used a 3R planar robot manipulator,
Okay.
which means it has 3 rotatable joints.
So lots of ways to move.
Yeah.
But finding the fastest one is the challenge.
Exactly.
What did they learn from those simulations?
Well, they ran the simulations with 10 different starting positions
Okay.
to see how the algorithm would adapt.
Uh-huh.
And on average, the optimized trajectories were about 38% faster than the initial unoptimized paths.
Wow.
Some runs even showed improvements of over 50%.
That's significant. So even though it might not always find like the absolute best solution,
Right.
it consistently delivered really impressive results.
Yeah.
And importantly, the robot could still perform the task accurately
Yeah.
while moving much faster.
You're right.
Did they visualize how the algorithm adjusted the robot's orientation?
They did. They plotted the initial and final configurations of the robot's rotation around the curve's edge.
Okay.
And it's fascinating to see how even these small changes in orientation
Yeah.
can lead to such dramatic improvements in speed.
So they proved the concept in simulations.
Right.
What about the real world?
Yeah.
How did it perform on an actual robot arm?
Well, they took their algorithm out of the virtual realm
Okay.
and tested it on a real UR10E robot arm,
Okay.
using a 3D fan blade this time.
All right, so they upped the ante a little bit.
Yeah, they did.
They weren't just content with a simple two-dimensional path.
Right.
What kind of constraints did they impose on the robot?
Well, they imposed strict error tolerances for both the Cartesian position and the angular orientation.
Okay.
So the robot not only had to follow the path accurately, but it also had to maintain the correct orientation
Makes sense.
throughout the movement.
It's one thing to move quickly,
Yeah,
but it's another thing to move quickly and maintain, like, perfect form.
exact.
Did they stick with the constant velocity assumption for these real-world experiments?
They actually tested both constant and non-constant velocity scenarios.
Smart. So they wanted to see how versatile their algorithm was.
Yeah.
Let's start with the constant velocity case.
Okay.
What did those experiments look like?
For the constant velocity case, they ran 6 different experiments
Okay.
with varying initial conditions for that free variable,
Okay.
the robot's rotation.
So they wanted to see if the algorithm could handle different starting orientations.
Exactly, and still find the fastest path.
Okay, it sounds like they were really putting their algorithm through the ringer.
They were.
How did it perform?
It pathed with flying colors.
Great.
The results were incredibly impressive.
Okay.
They mirrored the success they had in the simulations. The optimized paths were on average a whopping 63.5% faster than the unoptimized ones.
Wow. That's even better than the simulation results.
I know, it's amazing.
And they achieved those speed improvements without sacrificing accuracy.
Right.
Amazing.
Yeah.
Did they encounter any challenges during those experiments?
Well, the main difference between the simulations and the real-world tests
Yeah.
was in the errors.
Okay.
They found that the actual errors were slightly higher
That makes sense.
than predicted in the simulations.
The real world is always messier than a simulation.
Always.
I imagine things like friction and sensor noise and just tiny variations in the robot's movements all contributed to those differences.
Absolutely.
But were the errors still within acceptable limits?
Yes, absolutely. Even with those real-world imperfections,
Okay.
the errors remained within the specified limits.
That's reassuring. It's a testament to the algorithm's robustness, its ability to handle the unexpected and still achieve its goals.
Right.
What about the non-constant velocity experiments? Did those throw any curveballs?
So for the non-constant velocity case,
Okay.
they again ran 6 different experiments, each with a different initial condition.
Okay.
This time, the algorithm was allowed to adjust the robot's speed along the path.
So they gave the algorithm more freedom,
Right.
which could lead to greater efficiency.
Exactly.
What were the results?
The results were very encouraging. While the improvement in this case wasn't as dramatic as in the constant velocity scenario, they still achieved an average speed increase of about 11.5%.
That's still a noticeable improvement,
Yeah.
especially considering that the unoptimized paths in this case were probably already pretty good.
Exactly. It highlights that even when there's not a lot of room for improvement,
Right.
this algorithm can still find ways to optimize the robot's motion.
It's like squeezing every last drop of efficiency out of the system.
Exactly.
Did they observe those same discrepancies between predicted and actual errors in the non-constant velocity experiment?
Yes, they did. They saw a similar trend to the constant velocity case.
Okay.
The actual errors were slightly higher than predicted, but importantly, they were still within acceptable bounds for the most part.
So overall, this bi-level optimization approach proved its worth,
Yeah.
both in simulations and in real-world experiments.
Right.
It consistently demonstrated its ability to significantly speed up robot motion
Yeah.
for tasks that require following a specific path,
Right.
all while maintaining accuracy.
It's pretty incredible.
It sounds like it could revolutionize many industrial applications.
It really could. It's a powerful tool that has the potential to transform how we use robots in everything from manufacturing to medicine to exploration.
Yeah.
It makes you wonder what the future holds for robotics.
Right.
If we can achieve these kinds of results today, what will be possible in just 5, 10, or 20 years?
It's exciting to think about it. This deep dive has given me a glimpse into the incredible innovation happening in robotics right now. And it's clear that researchers are constantly pushing the boundaries of what's possible.
Absolutely. And it's a testament to human ingenuity and our relentless desire to solve complex problems.
Yeah.
And it's not just about building bigger, stronger robots,
Right.
but about making them smarter, more adaptable, and more efficient.
Absolutely. And a huge thank you to your listener, for suggesting this deep dive. We loved exploring this fascinating research with you.
It's always a pleasure to delve into these cutting-edge topics
Yeah.
and uncover the hidden gems of scientific progress. We're constantly learning and evolving right alongside the technologies we explore.
That's the beauty of it all. And to all our listeners out there, keep diving deep, keep those brains engaged, and never stop exploring the wonders of science and technology.
Yeah.
Until next time.
So for the constant velocity case, they ran 6 different experiments.
Okay.
With varying initial conditions for that, free variable,
Okay.
the robot's rotation.
So they wanted to see if the algorithm could handle different starting orientations and still find the fastest path.
Right.
It sounds like they were really putting the algorithm through its paces.
Yeah, definitely.
What happened? How'd it do?
Well, the results were really impressive.
Okay, good.
I mean, mirroring the success they had in the simulations, the optimized paths were, on average, a whopping 63.5% faster.
Wow. That's even better than the simulations.
I know, it's pretty amazing.
So they achieved those speed improvements without sacrificing accuracy.
Right.
That's pretty remarkable.
Yeah, it really is.
Did they run into any, snags during those experiments? Anything unexpected?
Well, the main difference between the simulations and the real-world tests was in the errors.
Okay.
They found that the actual errors were slightly higher than predicted in the simulations.
Yeah, that makes sense.
The real world is always a bit messier than a simulation.
The real world always throws you a curveball. I imagine things like friction and sensor noise and just tiny variations in the robot's movements all contributed to those differences.
Right, all those little things add up.
But were the errors still within acceptable limits?
Yeah, absolutely. Even with those real-world imperfections,
Okay, that's good.
the errors remained within the specified limits.
Well, that's reassuring.
Yeah.
It's a real testament to the algorithm's robustness.
Right.
Its ability to kind of handle the unexpected and still achieve its goals.
Yeah, it's adaptable.
So what about those non-constant velocity experiments? Do those throw any curveballs?
So for the non-constant velocity case, they, again, ran 6 different experiments, each with a different initial condition.
Okay.
This time, the algorithm was allowed to adjust the robot's speed along the path.
So they basically gave the algorithm more freedom.
Right.
Which could potentially lead to even faster trajectories.
Yeah, that's the idea.
What were the results? Did it work?
The results were very encouraging. While the improvement in this case wasn't as dramatic as in the constant velocity scenario, they still achieved an average speed increase of about 11.5%.
That's still a pretty noticeable improvement.
It is.
Especially considering that those unoptimized paths were probably already pretty good.
Yeah, exactly. It shows that even when there's not a ton of room for improvement, this algorithm can still find ways to optimize the robot's motion.
It's like wringing out every last little bit of efficiency.
Exactly.
Did they see those same discrepancies between predicted and actual errors in the non-constant velocity experiments?
Yes, they did. They saw a similar trend to the constant velocity case.
Okay.
The actual errors were a little higher than predicted. But again, importantly, they were still within acceptable bounds for the most part.
So overall, it sounds like this bi-level optimization approach really proved itself, both in simulations and in those real-world experiments.
It did.
It consistently showed that it could speed up robot motion for tasks that require following a specific path, all while maintaining accuracy.
Pretty impressive.
Yeah, really impressive results.
It's exciting stuff. It could change a lot of things.
It really could. I mean, this research has given me such a glimpse into the future of robotics.
It's amazing what they're doing.
I mean, it seems like they're pushing the boundaries of what's possible.
Absolutely. It's inspiring to see that kind of ingenuity and problem solving.
It really is.
And it's not just about making robots bigger and stronger.
Right. It's about making them smarter.
Exactly. Smarter and more adaptable, more efficient.
And a huge thank you to you, our listener, for suggesting this deep dive.
Yeah, this is a great one.
We had a great time exploring this research with you.
I always love getting into these cutting-edge topics.
It's so fascinating to see where things are headed.
Yeah, it really makes you think.
And to all our listeners out there, keep those brains engaged, keep diving deep, and never stop exploring.
Keep learning.
Until next time.